Okay, fine. Yesterday class, we have discussed about all the operators. What is the arithmetic operators, logical operators, relational operators, shift operators, and then replication operator, concatenation, and then all these operators we have explained, right? Now, we are going to explain about the behavioral modeling. What is the use of behavioral modeling in our Verilog? Verilog, we have to design a complex designs, right? So then Verilog provides that some feasibility to design your Verilog like a your design like a simple designs that is by using high level abstraction that is similar to behavioral modeling. That behavioral modeling we have to represent some algorithms, whatever the specification we have. Okay, that is related to algorithms we need to represent. And then behavioral modeling, what are the things we are writing means if else conditions we are writing, if else, and then loop statements, case statements, all these things are implemented in behavioral modeling. Okay, so that is the purpose we are going for the behavioral modeling. And then simulation we are synthesizing, after that we'll go for the FPGA modeling. So just designing the hardware by using different abstraction levels. In that, most of the designers are using either data flow modeling and then behavioral modeling. Data flow as well as behavioral we are using. That behavior will tells you what is the functionality we are using in our design. Okay, that is the main usage of behavioral modeling. Okay, so that in behavioral modeling we are executing different type of execution like procedural modeling and then sequential modeling. Okay, so most of the things we are executing the procedural blocks. That procedural blocks means, so we are using wire as well as range, right? So wire is used for continuous type of assignments. Okay, so this continuous type of assignments means data flow model we are using. That data flow, whatever the keyword we are using, assign is the keyword. Okay, that assign will gives you the functionality of your design. That means any combinational circuits you are taking like y equal to a and b you are considering. So just simply you can use the word keyword like assign, that is related to data flow modeling. But same thing we are executing in the procedural model. So that procedural model we are executing the behavioral modeling of Verilog. Okay, that behavioral modeling will execute inside the always or initial begin. Okay, so these operators are used in the procedural modeling, right? So always and then initial begin. That means always always block is used for, what is the use of always block? So whatever the conditions you are taking and then whatever the simulation you are taking, that executes continuously. So it depends upon your condition of the statement. So because always is the statement, inside that always begin we are using some statements. Okay, so what are the statements we are using depends upon multiplexer you are designing. In that multiplexer, what are the inputs you are having? Inputs I1 or I0. Okay, these two by one multiplexer you are using means two inputs are there. Okay, if any time and then select line is also there. Okay, any time the select line and then I0, I1 is changes means your output will be changes. Okay, so that sensitivity list we need to mention inside the always block. Okay, always at the rate star you can represent it means that star represents that all the sensitivity list, whatever the ports you are using in your design, that defines all the sensitivity list. Okay, so that is the usage of always block. Okay, most of the cases in behavioral modeling, we are using this always block and initial block. Initial block is used in test bench side, and always block is always used in design side. Okay, see how it is executing, because always begin we are using, right? In this begin and end, what are the statements are there? All these statements are executed sequentially. Okay, one by one it is executing. That is the sequential execution we are having. And also check that sensitivity list. Okay, if sensitivity list is not there means, okay, throughout the simulation it is repeating. That means entire execute entire your design will be executed all the time. Okay, but you are mentioning any sensitivity list means that based on that sensitivity list it will be executed. Okay, I told you that 2 by 1 multiplexer, that 2 by 1 multiplexer having the inputs like I1, I2 and then different inputs like I1, I2, I3. If any time this I1, I2, I3 values are changes, then your output will be changed. Okay, so that is the usage of sensitivity list inside the always begin block. Okay, and then sometimes we are using combinational circuits, but we don't know our design is how much complex it is. Just you are explaining that whatever that 2 by 1 multiplexer, only two inputs are there, then you can mention all inside that always begin block two inputs I1 and then I1 or I2. In that way we can represent, right? But I don't know, I'm using different type of protocols like AXA protocol and APP protocol or MIPI protocol. Different signals are there, but all the time I need to represent all the inputs like here I1, I2, I3 and then output. Similarly, some frame start, frame end, line start, line end, and then SDA pins and SCL pins. All the pins are there. Maybe we forgot, right? So that is the reason we are going for star. Okay, this star is represents that all the inputs. Okay, whatever the inputs you are having in your design, all the inputs will be considered, and no need to mention the name of the inputs inside the always begin block. Okay, so that is the reason we are using this always at the rate star. Okay, and then so sometimes we are generating the clock, right? So that clock we are also using to we are also used to always clock. Okay, usually we are using the always for generating the clock. So clock equal to negation of clock, this is the clock generation. But we are generating the clock in the test bench side, that's why we are using some delay. That means every time I'm generating the clock here, 0 second 0, and then 5 seconds it is 0 to 5 it is 0, and 5 to 10 it is 5. Okay, my clock is always toggling every 5 nanoseconds. That means initially 0 and then 1, again 0 and 1, 0 and 1. In this way, my clock will be toggling. Okay, that is the syntax of this one. So always 5, the clock equal to negation of clock. That means 0 to 5 it is 0, and 5 to 10 is 1, and then 5 to 15 is 0 again, and 15 to 20 is 1. Okay, in that way we are generating the clock, right? So that is the usage of always in our design side and testament side we are utilizing. Okay, and this is the basic example for initial begin block and then always block. Okay, whatever the blocks we are using. See, initial begin is there utilized in testbench side. See, module TB. I am representing the register inputs and then register input 1 and input 2. Input 1 is a single bit and input 2 is a 4 bit. Okay, just I am assigning some values here and displaying that. Just example for initial begin. Inside that you can also assign any variables like I1 equal to 4 tick. So suppose I am mentioning 3 down to 0 for I1 also. Then 4 tick B1010 data we are giving. And then I2 is also 4 tick B1101 data we are giving. Based on that, it will do the operations and then display the values. Okay. See, I am giving the value like a binary format, but I am displaying in hexadecimal format. It will be converted. It will convert and then gives the data in the hexadecimal format only. Okay. So if you are using multiple initial begin blocks, sorry, Yeah, tell me.
In this presentation, you just want to mention that there become uh,
I'm not
sorry,
audible. Your voice is not audible clear. Can you repeat
is
again?
this fine, sir? Is this fine?
Ah, now fine. Okay.
So, in this presentation, we put
See, if we are using multiple initial begin blocks, we don't know the compiler which initial begin block is taking first. Okay, so don't use always multiple initial begin blocks in your test bench code, because I don't know this initial block is taking first, or this initial begin block is taking first, or this initial is taking first. I don't know. Okay, so that's why most of the test benches we are avoiding these multiple initial blocks. Sometimes we are using some display statements, like we are displaying our waveforms. Okay, whatever the code you are executing, I need to check the waveform. For that purpose, we are using the another initial begin block. Okay, so that means the previous code is executed, then only we go for the waveforms execution. At that time, we will use the another initial begin block, and don't use, see here I'm also executing one data, and here also giving the another input. Okay, so in two inputs I will give the single initial begin block. So these two initial begin blocks, I don't know which initial begin block is taking first. Okay, so that is the reason we are avoiding multiple initial begin blocks. Okay, and how we are terminating your design means by using dollar finish. Okay, this dollar finish uh, will execute once in a once in a time of simulation. Okay, so once it is executed means your termination, your simulation will be terminated. See here, time is 5 nanoseconds and then 5 nanoseconds, and your simulation will be executed at 6 nanoseconds. Then this may be not executed. Only 5 nanoseconds is executed, and then second one is not executed. Okay, so and then initial begin your dollar finish you are mentioning means, okay, before that how many delays you are giving in your test bench, you need to check that. Based on that, you need to give the more delay compared to that previous delay. See here, 5 seconds delay is a 5 seconds delay, total 10 seconds delay. But you are terminating your simulation at 6 seconds delay. Okay, so that means remaining 4 seconds is not executing. Something will not be executed in your design. Sorry, test bench code. Okay, this is the timeline of the execution. See, Jira simulation, all the initial begin blocks are start the execution. Okay. So sometimes I equal to 0 you are giving. So 0 time, first initial begin block is executed. And then at 5 seconds, this is the 0 time I1 will be executed. And then 5 seconds I2 will be executing. Okay, and then another 5 seconds it will be taking that initial 2 will be second initial begin block will be executing. I don't know the simulation will be executing this one or this one. Okay, just this is the timeline, but simulation will take any type of simulation. Okay, see here also we are getting the initial 5 nanoseconds delay in the first one, and then you are finishing at the 6 nanoseconds. That means you call the dollar finish at 6 nanosecond. Only first statement is executed, the second statement is not executed. That means this display only it is executing, then second display is not coming into your output side. Okay, so that is the multiple initial begin blocks, and then dollar finish usage in your test bench side. Okay, I have already explained that sensitivity list. Okay, so this will be the execution of the different blocks. Okay, initial means execute in once a time. Okay, so just you are starting initial begin, then it is executing all the statements at a time. Once in a simulation, it is executed. Okay, depends upon the delays, it will be taking time, but otherwise it is executing all the statements at a time only. But always is that executing infinite loop times. You are ending the simulation time, then only it will be terminating. Otherwise, it is still executing. I told you initial begin is used in the test bench side, where you are executing your test bench. What is the start point? This will tells you initial begin. Okay, and then always used in the RTL side. Okay, so here it will triggers at 0th time simulation. I told you. So at the 0th time simulation, like a function, it will execute 0th time simulation. Similarly, initial begin is also executed at 0th time simulation. So all the statements are executed at time t equal to 0 only. Okay. Here also it is executing 0 at time, but depends upon the sensitivity list, it will be repeating your execution. Okay. So this is the behavioral model, and I told you initial block, the 0 time. This is the flow of execution, and then which are see initial begin, always, and don't use always. Multiple always blocks are also. I told you always blocks are also. We are having multiple always blocks we are using in your design code means one is for combinational circuit, that means always at the rate star you are using for combinational circuit. You can use single combinational always at the rate. Okay, and don't use multiple always at the rates. Okay, and also always at the rate passage clock. So passage clock or negate reset we are used for flip flops. That means sequential execution. Okay, so sequential blocks execution purpose always at the rate passage clock we are using, and then always at the rate star we are using for combinational circuits. Okay, for all combinational circuits you will use single always block. For all sequential circuits you will use single always at the rate passage clock or negative reset. Okay, so that is the purpose. See, all the blocks are at starts at 0th time simulation and runs in parallelly. So then I don't know which is taking first. That is the meaning of we are taking multiple initial begin blocks. Okay, and also multiple always blocks we are taking means I don't know which one is executing first. Okay, clear? So these are the system tasks. I will explain them later. Dollar display, dollar monitor, dollar finish, dollar stop, all these things. Okay, dollar time. Just we will go for display purpose only. We are using the dollar display, and we have a regions, different regions. In which region is executing display and then monitor. I will explain the later slides. See, initially is execute once only, always executes repeatedly. Initially is used in test bench, always used in design side. Okay, delays are used to control your time. It is also used in test bench side. And then dollar finish are also used in test bench side. You where you need to finish your design, test bench code. For that purpose, we are using the dollar finish. Okay, remember these keywords. Okay. See, this is the procedural assignments. I told you what is the syntax of the procedural assignments. We are using some variables. Whatever the variables, why we are using the variables, it can store the values, right? Okay, it can store the values or expression. That is the purpose we are using the variables. And then expression or value we are taking. So procedural assignments are executing sequentially. So that is used in either initial begin block or always block we are using. So previous slide we have explained, right? Same thing we are executing here. And then different type of procedural assignments we are using, either blocking assignments and non-blocking assignments. Most of the time we are executing the procedural assignment non-blocking statements only. Okay, and then we are going for executing the non-blocking statements, that is in combinational circuits only. Okay, so that means data flow model we are going for blocking statements. Okay, and then sequential circuits we are going for executing the non-blocking statements. Okay, see, blocking statements how we are executing, how we are representing means equality symbol. Okay, just equal. Okay, whatever the variable name a, and then this variable name a, I'm executing the different condition like x and y. Some bitwise operation I am executing that x and y. So this is the variable storing this operation x and y. Okay, so see this all in blocking statements are executing sequentially. That means one statement is executed, then next statement will be executed. Okay, different statements we are executing one by one, and don't drive the same values at the same variable. Suppose x is equals to y you are taking, and then y is equals to x you are considering. Okay, so this will be assigned to x, and then x will be assigned to y. This will not be allowed in the blocking statements. At this time, we will get the conflict. That means x propagation error we are getting. Some race condition we are getting. Okay, so don't use that same variable. Suppose swapping variable you want to do means suppose x equal to some temporary variable you can take, and then temporary variable is equals to y you can take, and then y is equals to temp you can take. Okay, in this way the variables will be swapped. Okay, so that is the avoiding of race condition in the blocking statements. But non-blocking it is allowed because blocking statements are executed serially, and then non-blocking statements are executed parallelly. Okay, two statements are started at the same simulation time, then there is no problem in that execution of your non-blocking statements. Then you can write x equal to y and y equal to x. Okay, so non-blocking statements are represented with less than or equal to. Okay, less than equal to symbol is represented means okay non-blocking assignment. Clear?
Okay,
Yeah. So this is the blocking segment execution, immediate execution, and then this is the schedule execution. Depends upon the timestamp. Whatever the time you are whatever the time you are taking, that time is depending upon that. Okay. Actually, it is executed at the 0th simulation time, and then update the time immediately. Suppose you are giving the blocking assignment statement, so whatever the output you are expecting, whenever you are giving the input, you will be getting the output immediately. So without timing, without waiting for the time. See, you can get the race condition. Okay, race condition why we are getting means so same variables are executing at the different time. So then you are giving the same variables, assigning the same variables at the twice time. Then you will get the race condition. Here we are avoiding the race condition here. Most of the combinational circuits I told you, combinational logic circuits, and then blocking statement, non-blocking statements are executing for sequential logics like registers and flip-flops. So this is the representation of blocking statement A equal to B, and then A less than or equal to B is representing for non-blocking assignments. Okay. See, what are the race condition possibilities I'm explaining you. So this is the display you are giving. Initial begin, you are giving the some data here, and then same another initial begin block y equal to data equal to y you are giving. Same thing we are assigning that. Suppose y equal to data you are assigning, that data will be assigned to y, and again the same data, same y data you are assigning to data. That is not possible. Then you will get the race condition. Now you need to avoid that race condition means you want to use some delays in your execution time. So that means y equal to data is the initial begin block, and then displaying the one statement, and after that another begin block we can use that. So then final data you can get that two outputs differently. Okay, so that means you are assigning data to y in the one initial begin block, and then other initial begin block. So this is the block 1 and block 2. Okay, so it is executing differently. See here initial begin is there, initial begin is there. So then two initial begins are executing at the same time. I don't know which data I need to consider. Then conflict may occur. That is the race condition possibility. And if you don't want to use this block 1 and block 2, then go for the non-blocking assignments. Then y less than or equal to data and then data less than or equal to y. In this way, we can avoid the non-blocking statement. See, that is the non-blocking assignment is the only one solution to avoid the race condition. Okay, clear?
Yes.
See, non-blocking for procedural assignments, I told you, right? So, what are the values we are explaining in the non-blocking statement? Same thing will be there. So, different regions we are having. In these regions, active region is there, and then non-blocking region is there, and then inactive region is there, and then postponed regions are there. So these different regions we are executing. See, non-blocking region is executing at the middle of the statement. After execution of active region, then we are going for the NBA region, non-blocking assignments. Okay, so this non-blocking assignments after the times after the execution of active region, then we go for the non-blocking assignments. See, in this active region, blocking statements are executed first, and then dollar display statements are executed next. Okay, all these things are executed, and then in active region, the right hand side of the non-blocking statements is executed next. Okay, so I will explain these regions later. Okay, we will explain in clear whatever the regions we are having in our Verilog. Four regions are there: active region, non-blocking region, inactive region, and then postponed regions. Okay, that is monitor regions we are having. See, same thing we are also continuing in this blocking and non-blocking assignments. So this is the example for non-blocking assignments. Previously we are taking the blocking assignment, and now all the statements are executed in parallelly. So that means all the statements are executed at the same time. Depends upon the differential delays we are giving. Based on the delays, it will be executing at different time units. See, time d equal to 0. What is the data we are getting? Data 4 we are getting. That is the value you are getting. So value of I equal to 4 you are assigning. That is the related to data value. Okay. So 0th time and then R value, I value, data you are assigning that. After time equal to 1 second, same data will be repeating. After the time 2, then you are giving the another data. Okay. Based on the delays, we are getting the different data in your output side. Okay. Suppose in blocking assignments you will get errors means that means race condition means how to avoid that race condition. Another way also there that another way we are using hash zero statement. Hash zero statement means so x equal to y is the one statement and y equal to x is the another statement. Before that you can use the hash zero. This hash zero is the region called inactive region. So this will execute, both the statements are executed at the same time, but little delay will be provided. Hash zero statement is there, that delay will be, so this statement will be executed some slight delay, like a light speed of delay, it is there. Okay, so we can't see that delay, but executing at the same time, we are avoiding this race condition by using hash zero statement. Also, we are adding at the second statement. That statement will be executed at the same time. Okay. So this is the step-by-step execution of your statements, whatever the values we are giving. R value will be executed at the 0th simulation time because R value, I value we are giving at the time t equal to 0 only. So then NBA region will be scheduled here only. And then there is no change because one time in is also no change. Same values will be there. And then time 2 is there, right? So this is the time 2, delay time 2. At that time data value is changed to 5. Okay, so this data value is changed and then remaining values will be same. Okay, same values will be displayed here because this dollar monitor continuously capture whatever the values you change. Okay, so dollar display means just whatever the value you are displaying, that value only display. But dollar monitor you are using means that dollar monitor always changes is captured. Okay, always captured, it changes. Whenever you are changing the input values, it will be captured. Okay, so that is the dollar monitor purpose in your non-blocking assignments. These are the differences I told you in the previous slide. Okay, so what are the differences we have? And then how to avoid how race condition we are avoiding. I told you, right? So we need to give some delay in the non-blocking statements also. Multiple initial blocks you are using, and you need to give the some delay to your display statement. Then this will be avoided. Actually, don't use multiple initial begin blocks while you are using non-blocking assignment. Single initial begin block is enough. But sometimes you are using multiple initial begin blocks in the non-blocking assignment. You can use some delay. Okay, that delay will be avoiding your non race condition. Okay, anything else here? And then implementation of sequential circuits. What are the things we are executing in the non-blocking statements? The D flip-flop I am considering. What is the D flip-flop operation? Just input, whenever the input is giving, same output we are getting. So that means D is equals to 0, and then that means your next output D is 0 means reset condition. Reset condition means your output is always 0 only, and D is 1 means set condition. Okay, set condition means whatever the input you are giving, same output I am getting at the output side. Okay, your output should be 1 here. And then you are giving unknown value means no change state. Okay, so same value will be getting. That means unknown value you are getting. Okay, so this is the D flip-flop operation. Then how the D flip-flop will be assigned in the non-blocking statements. See, this is my design code, module name. What are the inputs I am having? Reset pin is the input, clock is the input, and D is the input. Okay, clock, reset, and then D, all three are inputs, and output is the Q. So Q will be storing here. See, this is the asynchronous reset condition. Asynchronous active low reset. This active low reset means you are giving 0 means this condition will be operating. That means your design is in reset condition. During reset condition, all the values should be 0 only. Your output should be 0. Your output should be Q value should be 0. Okay. Here I am utilizing the active low reset in my always block, but I am giving the condition like if not reset 10. Not reset 10 means this is the active high reset. That means you are giving the value 1 means then you are in reset condition. You are giving 0 means evading releasing that reset condition. That means desetting the reset condition. Then I am getting the else condition like D equal Q equal to D. That means every value will be captured by the output. Whatever the D value changes, that will be captured by the output side. Okay, clear? This D flip flop design code. Same thing I'm testing through test bench module TP, and then in your TP we need to mention all the ports. Okay, in test bench there is no input and output ports. That's why we are representing only range and wire. Whatever the input ports we are using in the wire, so that should be represented at the range in the test bench side, and whatever the output we are representing in the design side range, that should be represented at the wire in the test bench side. And this is the DUT instantiation. What is this DUT instantiation? Position based or name based? Okay, this is the ordered based, right? Or position based, because clock, reset, D, Q, whatever the order you have considered in the design side, same order is considered at the test bench side. Okay, DUT means design, design under test. See your design, your hardware, we call it as DUT, design under test, or RTL, register transfer label, or we can call as hardware. Okay, all are same. Hmm. Yeah, input some log, you can represent that data type, wire data type. Okay, or sometimes you can use input only without using wire and range. Okay, but output you need to represent the range. Okay, because inputs default values are wires only. Okay, if you are not mentioned means the default it will take net type. Okay, wire only it will take. Okay. In the test bench, we can reverse because I told you in the ports representation, wire is used input side. Okay, initial inside the initial begin inside the world you can use the wire only input side, and then external world you can use either wire or net type. Sorry, rich type. Okay, net type or rich type you can use. Most of the cases. So most of the time in the test bin side, we are storing because the output is not storing any value. We are capturing the values only. That's why wire only we are using at the output side. And then in the test bin side, you are passing the stimulus. That means you need to store the values. That is the purpose we are using the range. Okay. And then what are the things we need to write in the test bin side? After the instantiation, generate the clock, always at the hash 2, clock equal to negation of clock. And then, so initial begin, inside the initial begin, during reset condition, all the values should be 0. And then, see, here you are using active low reset, active high reset, but here you are using active high low reset. Okay, don't use two different resets in your design is different reset and then test bench is defined a different reset means you may get reset problem. Okay, so that's the reason don't use that active low reset in your design set. Most of the cases active high reset only we can use. Okay, whatever the reset you are using in your design set, same reset you can use in the test bench side also. Otherwise you will get the reset condition issues. I told you repeat of 6. Okay, repeat variable. How many times you want to repeat your values? Okay, 6 times I want to repeat that. And dollar random range. This is the minimum value. This is the maximum value. In between that 0 and 1 only, it is repeating. It is giving different values. Dollar random means randomly generating the values. So that means 0, 1, 0, 1, 0, 1 is generating randomly. Sometimes 0, 0 is generating, sometimes 1, 1 is generating. Okay, depends upon the condition, it will be generating different random variables. Okay, random numbers. After that, I'm setting the reset condition again and then de-setting the reset condition after that some time unit. Then again I'm changing the values. Okay, so different values I'm giving them. See here also I'm giving the different values. Here also I'm giving the different values. So every time you are giving different values means you need to set the reset condition and then de-set the reset condition. During reset condition, all the values should be 0. During the de-setting the reset condition, manually we only give the values. Okay. This is the waveform representation. $dump files dump.vcd variable change declaration will be considered here. And dump variables means how many variables you want to represent. So sometimes you can take 0 or sometimes you can take empty or fewer times you can take 1 also. Okay. So this will indicate that your waveform. This waveform will be appeared in the output side. Based for the purpose we are using $dump files. Okay, dump files and dump variables for displaying the waveform at the output side. For that purpose we are using. Okay. See, this is the positive edge triggered the flip-flop synchronization. See, what is the difference here? This is the asynchronous reset. Based on the reset condition, it is executing. Here, positive reset is used. Positive edge reset. That means event-based D flip-flop we are designing. There is no reset condition here. Okay, just don't depending upon the reset condition. Depends upon the clock edge, that means depends upon the time delay it will be capturing the values. That's it. This is the asynchronous reset. This is the positive edge clock reset we are using. Okay, that means synchronous clock we are using. This is asynchronous reset we are using. That means there is no clock here. Here the clock will be playing the key role. Okay. So these are the Verilog procedural assignment guidelines I told you. And the non-blocking assignments, we can use it for flip-flops and then sequential circuits and latches purpose only. We are using the non-blocking assignments. And then blocking assignments always we are using for combinational circuits. And then non-blocking is the sequential circuits. We can use the always and initial blocks. Okay, these keywords already we have explained, right? And then sensitivity list. A synchronous reset means posage clock and negate reset we are using. Okay, posage clock or negate reset. Synchronous reset means only posage clock we are using. Reset action is immediate, is depends upon the clock edge. Okay, because based on the reset condition, asynchronous reset is operated. Here, clock edge on based on the clock edge we are executing. And then, example we can use that means if you want to reset your program at that time, you can stop any program, then you can go for the reset. In between the reset, we have operated right. At this condition, I am resetting my, and I want to go to initial condition. At that time, reset will be used. Some power off condition and some emergency stop condition, we are using the synchronous reset. And then clock edge, so it is used to pipelining operation. That means one clock is executed, then next clock is executed. Whenever the passage of the clock is there, at that time your simulation will be executed. Okay, clear this one. Yes. uh, this is the quick reference, always at the rate passage clock or negate reset. So that means sometimes you are executing your flip flops with passage or negate also you can execute. If you are considering negate in your design set, passage you are considering at the test bench side. You are considering in the passage in the design side, you can consider the negate in the test bench side. And then not executing at the same passage clock, the test bench and design. Okay, you can use the different passage and negate of your clock. That means effective utilization of your clock. Okay. Okay, fine. So these are the procedural timing delays. What is the delays we are using? We are using regular delay. Regular delay always go for hash. Okay, hash 5 and hash 2. In this way, we are going for regular delays. And sometimes event controlled means at the rate posage clock, at the rate negate clock. In that way we go for the delays. Okay, so most of the time we are going for the regular delay. In this we have two types of delay, intra delay and inter delay. Okay, inter delay means that is the regular delay. That means outside the variable we are representing the delay. That means you are giving the input 0 at time, but you are getting the output at 5 seconds delay. I am giving the input at t equal to 0 only. Okay, here only I am provided my input, but your output is executed at that 5 seconds delay. That means whatever the time delay you are having, that will be added to your delay. Okay, here I am taking hash 5. That means 5 seconds delay is updated here. That is inter delay. And then intra delay means within the variable we are giving the delays. Okay, that means x equal to y you are considering. This y will be assigned to your output side after 5 seconds delay. The previous case, we are giving the input 0 time, but you are getting the output after the delay execution. Okay, now here we are giving your output should be executed at time t equal to 0, but your input will be assigned at time seconds delay, so 5 seconds delay. This is your evaluation time t equal to 0, but ultimately you are getting at the output at 5 seconds delay because see, you are giving the input, so but I am receiving with some delay. Okay, so based on the delay, intra delay will be executed. Inter delay means you are giving the simulation, you are giving the input at the 0 time, but I am producing to other person, I am taking some time delay. Okay, So based on that external delay you are giving. That is regular delay. Regular delay is represented with hash 5, hash 10. This delay we are giving the regular delay. In this regular delay, we have intra delay and then inter delay. So zero time delay we are executing means hash 0 we are giving that. Hash 0 means within the same delay is executing. Without any delay it is executing the value. Okay. So all the statements are executed at the zero simulation time only. That means hash 0 time delay only it is executing. Whenever you are assigning some delay, so here I am executing 5 seconds delay. This statement is executing 10 seconds delay, and then this statement is executing 30, 20 seconds delay, and then post statement is executing 30 seconds delay. So whatever the delay you are giving 10, 20, 30 based on that delay, it is executed. It is appear at the output side. Okay. See regular delay, intra delay, and zero delay. Okay, three delays we are having. In this, we are also having some minimum and maximum. That means rise time delay and fall time delay is also there. Okay, so rise time delay means it is changing from 0 to 1. Okay, at this time some delay will be there. That is rise time delay. And then you are going down. Okay, that means high time to low time reaching we are having some delay, that is fall time delay. Okay, so sometimes we need to represent some rise time delay and fall time delays are also executed here. Okay, so that's what expression minimum and maximum. Okay, that is the minimum delay and maximum delay we are giving. Okay, and then event control means depends upon the passage clock or negate clock we are giving, right? So that is the event control. Okay. So event control sometimes we are having name event control. Based on the name we can give the event, and sometimes we are giving the level sensitive. That means either passage clock or negate clock. Based on that event control will be appeared. Okay. So named means we need to mention some name. See, so this is the regular events, either passage or negate. That means always at the rate passage clock you will be assigned. So then your description output will be appeared at the passage clock. Sometimes we can take the negate clock, and sometimes we will take the asynchronous reset condition also. Okay, combination circuits are also we can use executed in passage clock, and then negate clock. This is all our regular events. Okay, based on that clock only it is executing. Okay, so then event control means we need to mention some names. Based on the names we are executing. So what is the names is there? See, name-based event control where you are executing means event e done. Okay, this e done when you are representing e done. So I am triggering this event. Okay, here I am triggering the event. Then this will be executed. This event will be executed. This is the triggering event, and then waiting in event. That means I am representing the event name e done. Okay, so e done will be appeared whenever the e done will be appeared. Then only it will be executed. Why we are taking this wait condition means, see, wait condition if condition both are same type, but if condition if it is true, then execute the true statement. If it is false, then execute the else statement. But wait condition is not like that. So wait, then event, whatever the e done is there. So e done equal to 2. So that means two statements, two events are executed based up to that it will be waiting. Otherwise, it will not come out from the loop. After completion of the wait statement only it is coming out from the loop. Okay. So that is the wait statement we are using. That is the wait event. And then triggering event means, see here events E1 and E2. I am triggering the event 1 at the 5 nanoseconds and event 2 at the 15 nanoseconds. I am triggering that. So then at the rate E1 and then at the rate E2 I am considering that. So this event will be waiting. Okay, this is the waiting for E2. So whenever E1 is triggered, okay, then E1 will be executed. Whenever E2 will be triggered, that means 5 seconds delay, E1 will be triggered, then display statement will be executed. And then after 15 seconds delay, E2 will be triggered, then second display statement will be executed. Okay, so based on that event based, which one is executed and which one is not executed, name based events which will be telling them. Okay, so in this name based, triggering is there, and then event based is there. Okay, event based means whenever the event is there, that means wait for the event to complete execution. And then triggering means it is triggered somewhere. We need to mention initial begin block. Before the initial begin block, we need to mention the variable names. Okay, so based on that, that event will be triggered. Okay, see, uh, this will be the event triggered. Okay, see, the event is triggered at the initial time delay. Okay, so this time delay only, at 5 seconds delay only, this event 1 is triggered, and then event 2 is triggered at the 59 seconds, and then wait for completion of E1. So at 5 seconds delay, E1 will be completed, and then at 15 seconds delay, E2 will be completed. Okay, so that is the event control based. Okay, and level sensitive control, I told you that event wait condition. See, wait condition, wait equal to 5 is there. Okay, if wait, okay, condition I am giving that counter equal to 5, that means up to 5 counts it is executed. See, 1 2 3 4, up to the 5 counts. Whenever the 5 counts is reached, your wait statement will be unblocked. Okay, up to that it will be stay in the loop only. Okay, that is the wait statement. Sometimes they will ask you, I want to execute five statements are there. In that, only three statements only you need to execute it. Okay, so then this event based triggering is used. Okay, so I am executing, I am giving that E done. This E done will be some counting based. So this E done will be reaching to 3, then that means your count is reaching to 3, then you need to execute the event. Then remaining two statements I don't want to execute it. Only three statements only I want to execute it. Okay, at that time this wait statement will be useful. Okay, so here you need to initiate the event condition, and then wait condition, some counter is also used. Based on the counter also you need to execute that. Okay, after reaching the counter 5 seconds, then my loop will be executed. So sometimes they will ask you, my statement will be repeating 5 times. After the 5 times, you need to execute the loop. At that time, the counter is taking, and then wait statement you can consider. That wait statement, if you are giving the wait statement and then count value should be equal to 5, then you will be executing from exit from the loop statement. Okay, or sometimes event based, name based events are there, right? So at that time wait statement I will consider, that condition will be executed. Okay, say four statements are there. In that, only two statements I want to execute it, remaining two statements I don't want to execute here. At that time wait statement will be considered. Okay, with the name based event. Okay, so this is the event control description. Whatever the delays we are having, and then event controls are there. Okay, here. Yeah. Okay. Okay. So next one, this screen is visible, right? So next one is tasks and functions. How we are executing the tasks and functions in our Verilog. Okay, task will be executed at um, with delays we can execute it. Okay, functions it is executed zero simulation time. Okay, whenever you are using the functions, it will be executed at the zero simulation time. Okay, so that means whenever you are using function, some function name of the function, and then some ports list input and then output you can execute. After that, return value will be there. Okay, function will be returning some value. One value it will be returning. In Verilog, all the functions we are executed at the Jira simulation time. But task not executed at the Jira simulation time, it will be repeating that. Okay, in between the task and any task, it will be executing number of statements, and it is also allows the delays values here. And then functions not allowing the delays here. Okay, only see what is the function represented. Output I am representing output C output equal to C plus add of function int one comma int two. Okay, input 1 comma input 2. So this is the basic function. That means function can call functions. Okay, functions cannot call tasks. Why? The reason is tasks are executing at with delays. Functions are not what it- not allowing the delays. Okay, that is the purpose. Functions only call the functions. Any function call any function. See one function here I am calling the add function. We are declaring add function somewhere else. We are calling in another value. Okay, so that is the functions representation. And then tasks we are allowing the timing delays, and then either delays either posage clock or negate clock and wait delays, and all the delays will be executed in the task and end task. In this function, in between the function and end function, without allowing the delays here, cannot include the delays in the functions because delays all that are not executed in the functions. Okay, so that's why functions at Jira simulation time only it is executing. That means all the statements are executed at the time delay t equal to 0 only. Here the delays will be mentioned depends upon the user. Okay, user can mention 10 seconds delay in the one statement and then 20 seconds delay in the second statement. Based on that it will be executed. Okay. So this is the functions and task differences. Just see the differences. And then these are the examples for the functions and tasks. See how we are executing the functions and tasks here. So module adder is there. In this adder, I am representing two inputs A and B, and then outputs task output and function output. So in this initial begin, I am executing function output. So that adder function is calling here. Okay. Somewhere you are calling the adder function where you are see this is the f out, right? So this f out there here. Okay. This is the function output. We are giving the two inputs. Based on that, we are representing one output. That output should be adding here. Okay, so that this fan out function, that means function output function I'm calling in my test bench side. Then whatever the operation is executing here, that will be coming here. Okay, and similarly task added task. Okay, task can call function as well as task also, but function cannot call tasks. It call only functions. Okay. See here also I am representing added task. Some temperature or temporary output I am representing, and then output two and inputs are also mentioned. So here only I am mentioning the operations of addition operation and subtraction operation. It will be executed. Okay. So just adder and subtractor of the function we are executing adder and subtractor by using task as well as function. Okay. So I told you that timing control statements delays, wait, and event. So that is already explained, right? And in this inertial delay. what is mean by the inertial delay? Sometimes inertial delay will be there means in your input side, so hash 10 is there. Okay, so that means input is assigned to output, but output is executing at 10 seconds delay, later than 10 seconds delay. And then inertial delay, whenever you are having the less time delay, that means hash 10 is there, right? So this 8 to 20, 10 seconds delay is there. Below the 10 seconds delay, whatever the delays are there, all are vanished, all are erased. That will not appear in the output side. T equal to 1 and T equal to 6, this will be not executing. So this 5 nanoseconds is not executing at the output side. And then 2 nanoseconds time is also not executing at the output side. Only above the 10 nanoseconds, that only or below exactly 10 nanoseconds only allowed in the transport delay, sorry, inertial delay. Okay. So this will be only executing, and this delay will be executing after 10 seconds delay. This is the 10 seconds time t equal to 8. Then you can add plus 10 to this delay. Then 18 seconds delay it will be taking to get your output. Okay, that is the inertial delay. And transport delay means every time we are adding the delay. That means, see, in intra delay we are assigning 10 seconds delay we are assigning to the input delay. So every time this will be added to your input delay. So because your input will be assigned to output after 10 seconds delay. Then 1 plus 10, 11 will be there. 10 plus 6, 16, 18. Okay, based on that, the time is increasing here. Okay, so this is the Verilog model for delays, inertial delay and transport delay. So this inertial delay we can also call as regular delay, and then transport delay we can also call as intra delay. Okay. Wait statement I told you, right? Wait statement is depends upon the condition. See here, c equal to 5 is the waiting. Then after that only this statement will be executing. Output a equal to b will be executing. Here c equal to 0, this statement is not executing still. Whenever c equal to 3, so still this statement is not executing. Whenever you are reaching that c value is 5, then only the output a equal to b will be executing. Up to that this loop will not be terminated. Okay, so that is the wait statement uses. And then event based, I told you that event based, either name based and then triggered based are there. So event based either posage clock and then negate clock. Based on the posage clock and negate clock we have used that event based controls. Every posage and negate clock it will be changing. And then types of coding execution in procedural blocks, sequential execution. Sequential execution means one statement is executed, after that next statement will be executed, and then next statement will be executed. Here, sequential statements, the time unit will be increasing. See, here one time delay, this one time delay is added to this one, 1 plus 1, 2, and then this one is added to 1. Then at 3 time units delay, all the statements are executed because sequentially it is executing. I am taking 1 seconds delay, the same 1 second delay she is also taking, then 2 seconds delay will be taking place to reach that third person. Okay, and then third person is also executing 1 second delay, then 3 seconds delay will be maintained at the output time. Okay. So parallel execution means all the statements are executed at the same time. Fork join is used. In this fork join, whatever the statements are there, all are executed at the same time. That means, so this display one also executed at the same time, this display also executed at the same time, this display also executed at the same time. Then 3 units will be, every time unit will be one only, not adding the delay to the previous statement. Okay. So this is the file operations. We are opening the files and then closing the files in your operation. So if you want to open the file, you can use the $f open. Whatever the file you want to open, so then you can use the $f open. And then if you want to close the file, you can use that f close. Okay, my file write I'm opening here and executing some statements. After that I'm closing my file. Okay, so just file operations. If you want to go for the file operation, that is the usage of file operation. Sometimes you will call the read operation and write operation. So whenever you want to write the statements into your file, then go for the opening a file. Whenever you want to close the writing of operation, then go for the F close. This F close will be F close and F open will be writing a data into the file. Okay, and then reading the file into that data means you can use the read memory of data, dollar read memory of data that will read the data. Okay, whatever the memory data you are assigning, that will be reading here. Okay, file reading and writing. So these are the system tasks and functions. What is the use of system tasks and functions? I told you dollar time. Dollar time means whatever the current simulation time you are using, that will be appear at the output side. Okay, sometimes I'm using hash 10, okay, hash 15, okay. So this time unit I want to execute one display statement. This will be appear at the output side, and at this time I am using at the one another display statement. Then after 15 nanoseconds, another statement will be executed. Okay, that is the dollar time usage. It will returns the current simulation time where you are executing. That will be written by using dollar time. Dollar time means it is executing the floating values like 1.5 and 2.8 and 3.7. So in the time units or also we are having some decimal values that will be executed by using dollar real time. This is also current simulation time. It will be representing at the output side, but your time should be in some floating values will be allowed by the dollar real time. See, dollar stroke, why we are using the dollar stroke means whenever you are updating the last value, so I want to update my last value, suppose at hash 5, A equal to 5, and then B equal to 10, I am representing. After that, hash 10, A equal to 7, and B equal to 5. Okay, this last updated value I want to print. At that time, I am using the dollar stroke. Okay, dollar display, whatever the display values we are using, same values will be displayed here. You can use the dollar display means, so whatever the instant time you are using, this instant time you can use the dollar display means these values will be printed here, and then at this time these values will be printed here. Based on that, it is using the display statements. Okay, dollar monitor means continuously monitor your variables. Whenever you are changing the values, always see s equal to 3, this value is printing, s equal to 2, this value is printing, and s equal to 7, this value is printing, s equal to 9, this value is also printing. Every time you can change the variables means all the variables will be displayed by using dollar monitor. That's why instead of writing dollar display statement at every value, we can go for dollar monitor. So that dollar monitor will be displaying every value. That means A equal to 5 and then B equal to 2. This is hash 1. After that hash 5. Then A equal to 7 and B equal to 3. Okay, you can mention. Then this is also printing. And then hash 9. Okay, A equal to 3 and then B equal to some uh, 7. Okay, this value also printing in your output. This value is also appeared, this value is also appeared, and this value is also appeared. That is the usage of dollar monitor. So whenever the change is happening, all the values will be displayed in the dollar monitor. Okay. So dollar finish, I told you, you want to terminate your simulation, then you can go for the dollar finish. And dollar stop means it will not terminate the simulation. Just it will suspend the simulation. Okay, that like a pausing the video. If you are playing a video, you want to pause that video and then again you want to listen that video from the wherever you paused. At that time, dollar stop you can use. It will not suspend. It will not terminate your simulation. It will suspend your simulation. Again, you want to run the same code. You can go for that, resume that code, and then it will be executed. And dollar random means randomly you can generate the variables up to 32-bit variables. Okay, 2 power 32 values it will be generating. Okay, so 2 power 32 means is a sign values. That means 2 power minus 32 to and 2 power minus 30, 2 power 31 values it will be generating. That is the dollar random. Randomly it is generating the values. See, dollar random 5 value I am giving. So then it is printing minus 7 to plus 7. Okay, because here 16 values I am printing 2 power 4. That means 16 values. So this dollar random is executing negative values also minus 7 to plus 7. Then only 15 values you are getting. Okay, dollar $u random means unsigned variables. So here 4 bit I am taking 2 power 4 16 means 0 to 15 values. All the values are generating randomly in between that 0 to 15. Okay, so that is the dollar random symbol representation in your Verilog course. Okay, up to this you can study, and then tomorrow we can discuss these parameters and module instantiation already completed, right? And then stratified events we will go through it. Okay.